Hello, what we'll be covering in the next couple of videos are some of the sorting algorithms that the book goes through in chapter number 14. So the sorting algorithm rearranges the elements of a collection so that they are stored in sorted order. Selection sorts an array by repeatedly finding the smallest element of the unsorted tail region and moving it to the front. It's slow when run on large data sets. So in this example right here, what we're doing is we're sorting an array that has 5 integers. The first thing the selection sort will do will find the lowest value of the items in the array, and it'll swap out that position with the 0 position. So it'll swap out the 5 and 11 in the array. So what we have now is we have 5 and 11 have been swapped. So the next thing it does is it goes ahead and looks for the next smallest item in the array starting at position 1. So 9 is the next smallest item in the array, so it doesn't have to swap that item out. The next thing it'll do is it'll go ahead and look for the smallest in the array starting at position 2 towards the end. So 11 is the smallest, so it'll swap out 11 and 17, and then it'll move to position number 3. It'll look for the smallest item in the rest of the array starting at position 3, and what it'll do is it'll swap out the 12 and the 17. And then finally, when the unsorted position is of length 1, we are done. So the selection sort picks the smallest element and swaps it with the first one. Then it picks the smallest element of the remaining ones and swaps it with the next one, and so on. So what I've done is I've taken the 3 Java programs that the book includes, the selection sorter, the selection sort demo, and the array utility, and I've combined them into one class so we can go ahead and run that class in the Java visualizer tool. So let me just go ahead and open up JGrasp where I have that program. It's a little simplified because the amount of steps that it takes, the array has to be pretty small to go ahead and run it through the visualizer tool. So I'm just going to go ahead and do a Control A and a Control C, and I will copy it into the Java visualizer tool. And I will just go ahead and click on the Visualize Execution button. So what that does is it allows you to step through your code line by line so you can actually see how the selection sort works. So I'll just step through a few steps. So we'll go ahead, click on forward. Our array has been created. Our array name is A. We'll click on forward again. It prints out the array in the program output. And then now it calls the sort method. So the sort method will continue to walk through this loop, increasing I by 1 each iteration through the loop. And what it does is it goes in and it calls our minimum position. So what it's doing in the first iteration, it's passing I as 0 and our array as A into our minimum position method. So I'll click on forward. So now we're in our minimum position method. Up here at the top, we click on forward a couple times. It sets from equal to 0 and our minimum position equals to 0. And now what it does is it iterates through this for loop, finding the position of the item that has the smallest value. So let me just go ahead and click through this a couple of times. So the first time it's comparing it's incremented I to 1. Now it's comparing AI, which is position 1, which is 7. It's checking to see if it's less than our minimum position at 0, which is 9. and it is. So what it does is it updates our minimum position to 1 now. And it'll continue to iterate through this for loop. And then once it iterates through the for loop, it'll pass that minimum position back up to our sort. And then in this case, it'll pass a 1 back, and then the swap function method will get called, where the minimum position and the location at I will go ahead and get swapped out. So that continues and iterates until the array has been sorted. So you can go ahead and walk through the rest of that on your own using the code. The code that I'm going through, all the code examples will be posted out into Canvas. So the next thing they talk about is profiling the selection sort. They've created a stopwatch class that you can go ahead and measure the execution time of an algorithm. I will be going through that in a later video when we compare the selection sort to the merge sort using an array that has 100,000 items. So the next thing they walk through, or the next thing is just a chart. It kind of shows, graphs out the time taken by the selection sort as the array increases. So you can see that it has a steep incline as the array increases. The amount of time it takes also increases quite rapidly. So the next thing they do is analyzing the performance of the selection sort. So they're doing this basically to get down to something called the big O notation. Computer scientists use the big O notation to describe the growth rate of a function. In our case, basically what it reduces down is to n squared. You do not have to know how to do this, how to go ahead and reduce a function down to the big O notation, but it's nice to know what each one of the sort and search functions, big O notation is, and how they compare to other searches or sort functions. So if you did a Google search, I'm sure the big O notation for the popular sorting and searching algorithms could be found on the internet. So what we're gonna, so this next slide just kind of goes through some of the common big O growth rates: a constant, logarithmic, linear, log linear, quadratic, cubic, exponential, and factorial. The next thing they do is they talk about the insertion sort. We're not going to go through this via code. The insertion sort is the method that many people use to sort playing cards. You pick up one card at a time and insert it so that the cards stay sorted. The insertion sort has a big O of n squared also. So what we're going to go into more detail is the merge sort. So the merge sort sorts an array by cutting the array in half and then recursively sorting each half and then merging the sorted half. So it's dramatically faster than the selection sort. In the merge sort, one sorts each half, then merges the sorted halves of the array. So in this next diagram, what we have is we have two sorted arrays that make up one larger array. After they've been sorted, then what you would do is you would go ahead and merge the two sorted arrays into a single sorted array. So this is how it kind of works, the number of steps that you need to go through to go ahead and merge the arrays together. So again, I've done the same thing with the code that was provided in the book. I've gone ahead and created a class called Merge Sort Demo. So if we just go ahead and double click on that, and it's a very small array. It only has 4 elements in the array. If I do a Control A and then a Control C, Control A, Control C, and I drop it into the visualizer tool. and we will go through and walk through a few steps. You can go and actually walk through the algorithm that's used for the merge sort. So we'll just walk through a couple steps. We've created the array. We're going to do a print line. Next, we call our sort A method. And then what we're going to do in this method is we're going to divide the array up into two separate smaller arrays. So that's what we're doing in these next lines of code. So we have the first array divided into 5 and 1. And then we go ahead and create the second array, 3 and -1. And then after we do that, we recursively call sort passing in the first array. And then we go ahead and walk through until that array is finally, the first and second are sorted, and then we merge them. And then eventually what you'll get is the two smaller arrays will be sorted and they will be merged, which will produce our sorted array. So you can go ahead and walk through the steps after that. It's a good way to actually go in and understand how the code is actually operating. Okay, so when we analyze the merge sort algorithm, we get a big O notation of n log n. And the selection sort is n squared, big O notation. The merge sort is n log n. So the n log n function grows much more slowly than the n squared. So this next graph compares the merge sort timing versus the selection sort. So what we're going to do in the next video is we're going to go ahead and compare sorting an array that has 100,000 items using the merge sort and the selection sort. So we will talk to you later with part 2.